Here we will look at more examples of finding eigenvalues and eigenvectors. Two by two is always easy to find, at least to the point of characteristic polynomial. Finding roots depends on the polynomial, but quadratic polynomials are still easy to solve in radicals. Let's look at the case of 3 by 3. So here, at random, we will end up with a cubic characteristic polynomial, and finding its roots is not much fun, but carefully selected matrices will give still nice polynomials, and that's what, say, this is. It's a nice matrix in the sense that its characteristic polynomial will have nice, easy to find roots. What we have to do to write down this polynomial is to take the matrix, subtract t from its diagonal entries, and we will end up with these numbers on the diagonal. Well, not quite numbers, but polynomials in t, linear terms in t. Of diagonal entries are as they were, and then we are to compute the determinant of this matrix. And the preferred ways are row or column expansions, especially if we have enough zeros to make them short. The point is we have to factorize the result as soon as we can, and row expansions very often provide such possibility for factorization. So if we just take the first row to expand alone, we will have two terms, one for the first entry and one for the second entry, and the first entry comes with a cofactor, which is the determinant of this corner matrix with sign plus. And the determinant of that corner matrix is minus t times 1 minus t for the diagonal product, and then negative 1 for the off-diagonal product. So that is the cofactor. The cofactor for this entry is with negative sign, and it is the determinant of the 2 by 2 matrix of these 4 entries. And the determinant is just 1 minus t. And the element is 1, so we have it all. And immediately we have a factorization. So 1 minus t is the common factor for the two summands, and we can write the result as a product, and that's what we should not miss doing. We are to find the roots, and the polynomial is cubic, so if we can factorize it, that will reduce it to quadratic and linear, and then we are in business. The quadratic we are left with will have t squared with positive sign as a product of negative t and negative t. Then it will have negative t as a linear term, and then negative am I doing it all? I'm not factorizing, I'm not using this term in my computation, so there's negative 1 coming from the first copy of 1 minus t as a coefficient, and there's negative 1 from the second, so we'll have negative 2 total. And now we have to factorize these. So believing in goodness in the world, we'll have integer roots, and the product of them will be negative 2, and if they're integer, they should be divisors of 2, so like plus minus 1 plus minus 2, and then the sum will be positive 1. So the roots are negative 1 and 2, giving us these factors. And of course, I should have used the generic formula for roots of quadratic polynomial, but guessing them is always quicker. All we need is to check that this product is indeed the quadratic, and it is. Negative 2 is the free coefficient, t, and then negative 2t is giving us negative t as the linear term, and t squared is there already. So the spectrum of our matrix here consists of 3 numbers, and I will list them in the natural order. So it will be -1, the smallest, then 1, and then 2. And the matrix is with integer coefficients. Eigenvalues are integer. The eigenvectors, at least some eigenvectors, should be possible to realize is in just integer coefficients. So that is an also verification principle. So let's look at the first of our 3 eigenvalues, -1. To find its eigenvectors, we have to take our matrix and subtract this eigenvalue from diagonal entries. Subtracting -1 is as good as adding it. So we'll have 2, 1, and 2 on the diagonal. Of diagonal entries are the same as in M. And now this matrix has to be singular, and that is a checking point for this eigenvalue, that we found it correctly. And singular means that homogeneous system will have non-zero solutions. So let's find a reduced row echelon form of this homogeneous system. And the first transformation I would like to do is to put this at the bottom of my matrix and move the 2 to the top. So that will be a result of 2 row swaps or a row permutation in a cyclic way. The reason for doing that is because these 2 rows already have nicely positioned pivots. All I need to do is to try and eliminate the last row, and I can just take in row subtraction to eliminate 2, row 3 minus twice row 1. I will have coefficient 0 here, and then I'll have -1 here, and then I have -2 here, and now the resulting last 2 rows are simply proportional, so row addition will eliminate the last row, giving me a row echelon form. A row echelon form with 1 free variable, so I should have a non-zero solution. Reducing this row echelon form, I will have to subtract from row 1, row 2. Now I'm ready to write a generic solution. It will be 1 parameter space of solutions. The dimension of this solution space will be the number of free variables, just 1. It will be just 1 parameter family of solutions. All solutions are eigenvectors with eigenvalue -1, and they're all proportional to the one I'm to write. What I will do, I will choose the 3 variable, which is the last coordinate, to be 1, and then compute from these equations what are the pivots. And the first equation says that the difference of the first and last coordinates is 0, so that makes them equal. The first and last coordinates are equal. If the last is 1, the first is also 1. This equation says that the second coordinate plus twice the last coordinate is 0, so if last coordinate is 1, the second is -2. Let's continue. So the second eigenvalue in our list is 1, and then again, to find its eigenvectors, we have to modify the matrix, subtracting 1 from the diagonal. That will make these diagonal entries of diagonal entries are the same. And again, the matrix has to be singular, and now it is manifestly singular. We have 2 identical rows, so if we just move again the first to the bottom and do the row subtraction, which I will do in one go, we will have just these 2 rows left. And that is already a row echelon form, but not reduced. Reducing, I'll have to add to row 1, row 2. Again, looking at it as a system of equations that will give me all the information about coordinates of a solution. There is one parameter family of solutions. The solution space is one-dimensional. As before, last coordinate is a free variable. I can choose it to be whatever I like. I will choose it to be 1 again. And then the second equation says that the second coordinate is always 0, because that is just second coordinate plus nothing is equal to 0. The first coordinate is the same as the last with minus sign. So that is a representative of eigenvectors with eigenvalue 1. All other eigenvectors are proportional to this. And the last eigenvalue is 2. Subtracting it from the diagonal, we will have this matrix. And again, it should be singular. It's not that apparent anymore, but okay, again, let's put the last to the last place the first row. So we'll have these two pivots in places, and then some row to eliminate. And the first elimination is row addition. Which will make 0 here, which will create -1 here, and we'll still have 0 here. Now, what's going on? I'm not to change the row as it was. It was 1, -2, 1, so 1 has to be here. And then when I do row addition, I will create 1 here. And that is because I have to see a singular matrix, and that's how I saw that something was not carried accurately enough. But now the matrix is singular, which suggests that computations might be correct. And now to make it a rational form, we just eliminate completely row 3 by doing this row addition. Will be left with only 2 non-zero rows, and making it reduced, we will have the first row to have 1, 0, and then -1 as coefficients, and the second row is this. Writing a generic solution. Again, there is one parameter family of solutions for one free variable. Now the statements are behind this matrix that the sum of the first and the last is 0, the sum of the second coordinate and the last is also 0, so all coordinates are the same. If I make the last, the free, to be 1, then if I make it 1, then I will have all one vector. So that is the complete description of eigenvectors and eigenvalues. Any eigenvector is proportional to one of the 3. Any eigenvalue is one of this short list. Let's now look at another example where we will see that integers or rationals or even real numbers are not enough to find eigenvectors and eigenvalues. Because the characteristic polynomial will have no real roots. So let's take this matrix and write its characteristic polynomial, which is the determinant of this 2 by 2 matrix, and the polynomial becomes t squared plus 1. T squared as a product of negative t with itself, and then minus -1 gives us +1. So that is a polynomial which has no real root. And that is why complex numbers are so much better, because if we just to use real numbers, we have to stop here and say this matrix doesn't have real eigenvalues and so doesn't have real eigenvectors. Which makes a certain sense, because this is a matrix of rotation by pi, and then such rotation doesn't have any lines on the plane preserved. But nevertheless, if we can be comfortable with using complex numbers, we can find missing eigenvalues and eigenvectors, because in complex numbers any polynomial has a root or has all the roots. So we can factorize this polynomial according to its roots as t minus complex I, t plus I. The eigenvalues are, so now we don't have a natural order. Complex numbers are not really ordered, but we still can write them as, say, minus I plus I, going along the imaginary line bottom up. And then for each of these eigenvalues, we should be able to find corresponding eigenvectors. So let's look at the first and solve homogeneous system with complex coefficients. I'm subtracting negative I, so I'm adding I to the diagonal entries of my matrix. And yeah, okay, it doesn't look like it is singular, but we have to do row elimination. So maybe first swapping the rows, making it look nicer in the first column. And then to eliminate the second coordinate of the first column, we have to take this coordinate, multiply by the appropriate number the first row, and do the row addition. So there will be a coefficient, which is just I if I'm to add. And what will happen is that I'll have 0 here as desired. What will happen here, I have to compute. But what happens here is 1 modified by I squared. And I squared is -1, so I'm going to see 0 here, which is a good sign. It says that indeed this is an eigenvalue. The system is solvable with a non-zero solution. The only equation we have for this non-zero solution is that the second coordinate multiplied by I is equal to the first. So if I make the second coordinate 1, the first coordinate will be I. And that is the eigenvector for eigenvalue -I. And any eigenvector with this eigenvalue will be proportional to this. The story of I is very similar. We can do it honestly by again subtracting I from our matrix, again swapping the rows, and doing row subtraction, row 2 minus I, row 1, and maybe scaling the first row by minus sign. We will have 2 zeros. Please check it. And that will give us a vector which will have coordinates related in the following way. The second coordinate multiplied by I will have to be minus the first. So the second coordinate made 1 will make the first coordinate -I. But I could have written this answer straight away, knowing this answer for the eigenvalue -I. Because my matrix is real, so if I'm looking at the eigenvalue equation, or eigenvector equation, which says m times vector is equal to c times the vector, I can conjugate this equation, meaning I'm conjugating all the numbers in the ingredients of the equation, and m is stable under conjugation, complex conjugation, because it is all real, but the vector v will conjugate, and the c will conjugate, and the vector v again will conjugate. And so after conjugation, I will have this equation, and it is saying that the conjugate to the vector v with eigenvalue c will be an eigenvector with eigenvalue c conjugate. So these two, again, eigenvalues are roots of a polynomial with real coefficients, and they have to come in pairs, complex number and its conjugate. And that's how we can not do the second computation, but just take the vector and compute its complex conjugate and see the result. Or take the number and compute its conjugate and see the result. So complex computations are difficult, but with real matrices, if we are starting with them, we only need to do half of them, which is a good message. See you later.